Right. So, we continue with our development of the PML, and the concept that we have to keep in mind is that coordinate stretching is mathematically the same as generating a anisotropic medium, therefore it absorbs, right, it has evanescent waves. Okay. And the key idea was, as we already mentioned over here, we have generalized this del E and del H operator to now have a 1 by Ex, 1 by Ey, 1 by Ez term. Similarly for the H, 1 by Hx, 1 by Hy, 1 by Hz. Okay. As a result of which I got a new dispersion relation which is over here, and Maxwell's equations got redefined a little bit. The moment I put Ex, Ey, Ez all of them equal to 1, I get back vacuum. Okay. So, that is the condition. So far what we spoke about was just a simple one medium, right, in which it has some values of Ex, Ey, Ez, Hx, Hy, Z. But what was our original motivation? We wanted to put in an absorbing layer in our computational domain such that the waves did not get reflected back. So, for that we have to consider the interface between two media. So, that is what we will look at next. An interface between two mediums. Okay. So, how will we do this is, let us say that I have a xy plane is denoted over here, z is equal to 0 is an interface. Okay. So, this over here on top is region 1, this is z is equal to 0, and then I have region 2. Okay. And we will do a simple thing, we will consider a plane wave that is falling onto from medium 1 onto medium 2. Okay. So, for example, region 1 could be our computational domain, region 2 could be the PML layer. Okay. So, that is the setup, and I have some wave falling like this, getting reflected over here, and my goal is that this reflection coefficient should be 0 in the best case, right, that is what I want to design. Okay. Now, so we will deal with plane waves. Okay. So, now when you looked at this kind of a problem, I mean this is something that we have been seeing from high school, a planar interface and a wave falling over there. That is when we had derived the Fresnel reflection coefficients for two different polarizations. We had called it that back then, we had called them parallel polarization and perpendicular polarization, depending on whether the electric field vector is in the plane or perpendicular to the plane, right. So, I know that any arbitrary plane wave can be broken up into two orthogonal polarizations, but how I choose those orthogonal polarizations is up to me. One convention is parallel perpendicular, but that is not the only way. Another way could be TE and TM. Those are also two orthogonal polarizations into which any arbitrary plane wave could be written. I need not do perpendicular and parallel. Not exactly, right. So, what was the difference between, so for example, this was, okay, so this is E which is coming out of the board. Okay, so we will call this perpendicular polarization, right, but and the other case E will be like this, right. So, now there is, yeah, okay, they are actually the same. So, there is a non-zero Ez or not, that is basically the definition of TM and TE, whether non-zero Ez or not, fine. So, it makes life simple also. These are the two cases, but we will not use this perpendicular and parallel notation, we will just use TE, TM. Okay. So, in TM, what was our situation? I had HZ was 0, right. So, I had EZ, HX, HY, and then TE I had HZ, EX, EY, okay, and reality is a linear combination of these two, fine. Okay. So, what we will do is we will start with TE, okay, and derive something, and generalize, I mean to get the TM is actually even easier. Okay. So, we will start with this one, TE polarization. Okay. So, plane waves in two regions. I will start with the plane wave incident from region 1. What kind of waves do I expect? A reflected wave, transmitted wave. Those are the waves that I expect, right. So, this E incident, some vector E naught e to the minus j k, what should I call it, let us call it k I dot r, okay. And E naught in this case is going to be a vector in the xy plane, right, because it is Ex Ey, right. So, whatever it is, we do not need to specify it. Similarly, I will have the reflected wave, okay. So, E reflected, okay. So, this is going to be, so can I simplify the form of the reflected wave? So, the wave vector, I mean the electric field for the reflected wave, I can write it as some ER whatever, but is there any relation between the vector that I should write here and E naught? It should be, they should be in the same plane, right. So, I can write this as simply some R times E naught, and what do I write for this? Kr dot r, right. Kr is the reflected wave vector. There will be a simple relation between Ki and Kr which we will derive, okay. And so, this is reflected, this is incident, and then similarly I have a E transmitted, again the plane should be the same. This is a transmitted wave. Now, so when I try to use these equations, what is the one thing to enforce given these equations? How do I proceed further? Ei plus Er, what about Ei plus Er? No, systematically what can we use? What is the principle? Tangential boundary conditions which state that, because I mean in general that will not be true, but here it is true because no current sources are of course not there, but remember the boundary conditions are for tangential fields. Yeah, exactly. So, boundary conditions for tangential fields. My fields are already tangential because there is no z component, right. If there were a z component, that would be a normal component, right. So, since no z component, then I can write Ei plus Er, that is the field on the in region 1, that should be equal to Et at only at z equal to 0, okay. So, then what happens next? So, we will substitute these expressions inside. So, I am going to get, so E naught plus interface, z equal to 0 is the interface. Okay. Region 1 is defined by z greater than 0, region 2 is defined by z less than 0, top and bottom. Okay, so what will these, I mean I can cancel out the E naught from here, from all the from both sides. What else, what other further simplifications can I say from here? This is a bit of a revision of what you would have done in your undergraduate electromagnetics course. What can I say from here? The propagation constant? But can I say that by looking at this equation? So, for example, this equation, so Ki in general will have a x, y, z component. This interface is happening at z equal to 0. So, k dot r will only have a kx x k plus ky y, okay, the z equal to 0 term is gone. So, I cannot actually say anything about the z components, okay. What about the x and y components? What can I say? Because, I mean, what is the mathematical argument or reasoning from here? I mean, you can interpret these as phasors. These are phasors that are rotating, right. So, this should be true at z equal to 0, but if I take any point xy, it should be true, right, because the choice of origin is arbitrary. It's a plane interface, there's a wave hitting over here, right, and the wave is not a point, right, it's hitting the entire interface. So, this should be true at all xy, right, and you notice that this ki dot r, this is going to have terms like ki x x plus ki y y, and these phasors are rotating in whatever in phase space, and this expression should be true always. So, what is the only possibility for these phasors to rotate at the same speed in some sense? So, visualize this, right, the first is a phasor, second is a phasor, third is a phasor, right. As I change the values of x and y, what will happen? These phasors will change in phase. Now, I am adding two phasors on the left hand side and equating it to another phasor on the right hand side, and this relation should be true for all values of rotation. When will that be possible? When all the phasors are rotating at the same speed. Otherwise, sometimes they will be in phase, sometimes they will not be in phase, and this relation will not be true. So, when for the phase speed in some sense to be the same, what can I say? All these ki x's and all, they should all be the same, right. So, that is what is called in optics the phase matching condition. This is actually the rigorous way of deriving your Snell's laws. Okay. So, phase matching it is called, it's more like a common sense thing. So, ki x should be equal to k r x should be equal to k t x, and k I y should be equal to k r y should be equal to k t y. If I ensure this, then no matter what x and y I plug into this equation, the phasors will rotate at the same speed. Once this is done, what do I have to, I mean the immediate conclusion from here is, because the phasors are equal, they can get cancelled off, right. Right. So, this is at TE polarization, alright. So, it is clear what we did, right. Now, next is, so I have got one equation in two variables r and t, right. What do I do next? Well, wait, I mean one thing before that, you notice that this these relations over here, these taken together basically give you a Snell's law. Once you write your these k vectors in terms of angles, you will get your n1 sin theta equal to n2 sin theta, all of that comes from here, but we are not going that route. Next what do we need to do? Normal components. Is that a wise idea? When we derive our reflection coefficients from a planar interface, we did in the undergrad course, what did we do? We used tangential boundary conditions for both E and H, not normal boundary conditions. So, I have used tangential boundary conditions for E, next what remains? H tan, right. So, next is going to be H tan conserved at, this is actually how you derive your R for TE and TM polarization, right. The second equation comes from here and you just enforce it. Yeah, because z equal to 0 is the tangent to the surface. Well, it is in my hand how I design the surface, right, because I am designing the layer. So, I am going to, I will make sure that it is planar, but if it is weird, then it is weird, then it will only be a local condition approximately true. Yeah. The direction of yeah, That means even if the components are the same, the dot product So, the directions of the incident and the reflected wave vector are different, and that difference is primarily coming because of which dimension, x, y or z? Z, right? Incident is going in minus z, reflected is going in plus z, right? So, z is the guy who is making the difference, but z term vanished from this phase matching condition. Only at the interface. I mean, boundary conditions are anyway true only at interface. Okay. The z component of the wave vectors will be very crucial, we will come to it subsequently, but that is a good point. Okay. I mean, you have a wave vector that is going like this, if I flip the sign of the z component, it will just go up, right.